Good afternoon, Milad Mosallaei from Laboratory for Future Electronics. In the world of printed electronics, one of the most important topics is stretchable electronics. How do we make electronics stretchable? So we need both materials and design or geometry. Therefore, here, if in this picture, this is our lab, we have materials adaptable with stretching deformation like functional inks, basic and advanced functions, plus soft substrate. Inkjet and screen printing are the most common method for making the stretchable devices. I use screen printing. And about the application, healthcare application is one of the most important area thanks to the stretchable electronics. In this photo that Matti already explained and Tiina, my colleague, explains in more detail, you see that user wears the health patch, but if you notice, it's under continuous intention like mechanical or chemical. That's why reliability is very important. We do reliability like some basic tests like stretching, cyclic test to see the lifetime performance of the device. And also we analyze the system by DIC, which is very important because we can track the strain during the deformation, especially for the for modeling point of view. And here is one of the applications that we made, stretchable interconnects. So we use deformable materials for making stretchable interconnects, and we tailored the design by geometry, by finite element analysis. That's why we could get better performance. First one is the stretchability. The green one. It's the result with the better performance thanks to the geometry. And also this is, in the middle one is the cyclic test. Some groups, they don't use cyclic test, but since we want to mimic the real life performance of the application, we do the cyclic test. And also it is important to do the imaging because we want to see what happens to the device when it is under tension and deformation. Thanks for your attention, and if you have any question, please come to my desk.
Thank you, Milad. Give him a big hand.
So, hello everyone. My name is Tiina Vuorinen, and this short introduction is about printed electrodes for wireless ECG and respiration monitoring. A bit more than a year ago, my life as a new mom looked like this. And I think that from all those wires, it's easy to see why every day I hoped that the monitoring devices would look less like this and so much more like this. So, this is just one small example why there is a need for this new class of electronics called epidermal electronics. Epidermal electronics refers to wireless body monitoring systems that will integrate seamlessly with the skin. Here we have some inkjet printed temperature sensors on top of a normal transparent band-aid. In addition to temperature sensors, we are able to fabricate even more versatile measurement systems. For example, if someone is experiencing heart-related issues, he or she is often used to ask to wear this Holter monitoring system. Holter monitor is a portable battery-powered device that will have electrodes connected with wires, and these electrodes are then placed around your upper body. To improve the wearability of this type of a device, we have developed this printed electrode band-aid for 3-channel ECG and respiration monitoring. This band-aid has been fabricated using screen-printed stretchable silver ink with stretchable polyurethane substrate. The performance of this system has been verified both with healthy volunteers, but also with cardiac patients in collaboration with Oulu University Hospital. And the signal quality seems to be comparable with the signal quality received with the traditional electrodes used nowadays in healthcare. So printed electronics enables the use of completely new kinds of materials and structures to build these unobtrusive vital sign measuring systems. So if you had some questions and ideas about these topics or something else about body monitoring and printed electronics, please come to meet me at the desk too.
Thank you, Tiina. Big hand. Great work.
My name is Behnam, and today I'm gonna tell you shortly about a little bit about inkjet printing and inkjet printed circuits. First, I start with benefit of inkjet printing. For the conventional microfabrication, actually, and to deposit and pattern certain materials on top of our substrates, we usually use photolithography. And as we see on the left side, this process is containing many process steps. Here we need masking, a vacuum, we have waste material, it's costly. On the other hand, but we have a kind of good alternative named inkjet printing on the right side. And as we see, we have here just a couple of process steps, and we deposit the material exactly what we want. And then right after that, we have curing of the material. So basically 2 process steps. And here we don't have kind of masking process and vacuum. We don't need that, and it's much faster and more efficient, maybe compared with the traditional one. What we are able to do, we have commercial printers, inkjet printers from lab scale to industrial scale, as we see here from left to right. And the first one is the desktop R&D printer that we have. It's mostly for R&D, and it's the inkjet printers that we have at homes. But here we print functional materials instead, and the middle one is something in between R&D and fully industrial. And for the middle one is able to print with more than 1,000 nozzles, and NIR and UV curing agents are integrated in the machine, so it's really much better than the first one. So who could benefit from this inkjet? Since we have this range of substrates, from rigid to stretchable substrates that can be used for inkjet printing, we can say that this technology it has the potential to be used for different industries like microelectronic packaging, miniaturization, flexible electronics, soft and hybrid electronics, and stretchable electronics. So it was the end of the slides, so we can discuss later in more detail if you are interested. Thanks.
Thank you, Behnam. Give him a big hand.
Okay, I'm part of the American invasion. Don started it, and I followed him here. I started working with him in 2011. We went back through time with an Academy of Finland project together, and then that led to a Finnish distinguished professorship. So I've been here living on and off since November 2014. And when you go on the lab tour, you're going to see one of my students from Ohio State visiting here and working in the lab. So my colleagues, Matti and Don, have articulated this wonderful new opportunity for Internet of Things, overwhelmingly large numbers, largely silicon-free, printable, incorporating ambient energy harvesting that Don pointed out. But the one thing that they've not really talked about is, do we need these sensors, these autonomous units, to be energy thrifty? Because if they're only getting trickle charges from the environment, we need to be very judicious about how we're going to expend that energy. You know, if you ever have a laptop that you've run 3-4 hours and you're in the summer and you're wearing a pair of shorts, that laptop gets very hot. That is indicative of how much power you're consuming. We can't afford that. We want to make this very affordable. So here is the equation for a transistor. I'm not going to lecture to you. I lecture to my students. But most people are looking for the, wait, wrong way. Are looking for high mobility materials, and I'm arguing that we can generate the same performance by increasing the capacitance by using a very clever high K dielectric. This has been done in Intel microprocessors, and we're trying to replicate it in this modality. So we want energy thrifty for these energy constrained systems. So this is a duplication. This is one of Matti's slides, and I don't need to argue why we want to do this. It's everywhere and so forth. So one of the things we want to do is Finland invented ALD, and I'm trying to incorporate that into. I've been working with that, incorporating ALD since actually before my work here in Finland. And so I'm really happy that we just received a FIRI award that will allow us to put an ALD system integrated with our glove box, which will allow us to do some wonderful opportunities. So with that, we'd be able to do ALD with printing, very unique. And so that's the end. Thank you. I'll be at station 4 if you have any questions.
Thank you, Paul.
Hello everyone, I am Donato Di Vito from Tampere University, and I'm working on mechanical modeling and characterization of materials here. My main expertise comes from mechanical modeling of highly deformable materials and modeling of conductive inks and of stretchable electronics devices is one of the applications for these kinds of methods. Actually, there's a lot of interest growing in mechanical modeling of conductive inks. This is because modeling allows us to greatly reduce the amount of tests needed to characterize the material. It allows us to get localized information about deformation fields and how does the system behave with deformation. And on the long run, it will help us to predict the complex system behavior and give us some way to turn, for example, limitations into features by working on geometry and other properties of these materials. With modeling, we are currently doing that on 3 different levels. At first, we're working on getting the overall mechanical behavior of the different materials involved in stretchable electronic devices. With this basic knowledge, we can work on a macroscopic level to understand better how does geometry influence stretchability for these kinds of systems. And additionally, we are working on a microscopic level to understand if there are any possible connections between microscopic structure and macroscopic mechanical and electrical behavior for these materials. At each one of these different scales, we are actually facing very interesting and very new challenges. These challenges are mainly related to how do the different materials interact with each other for these systems? How can we describe the loss of conductivity for these materials that we are using, and how much can we actually push on geometry to get more stretchability and more deformable materials out from our stretchable electronic systems? If you're interested in the topic, I will be at stand number 5. Thank you for your time.
Thank you. Great work.